Hey, welcome back to STEM class, and today we're talking about waves. Do a little recap from last week, or from yesterday. We were talking about the different types of waves, and on those waves we had what we call a mechanical wave, which needs a medium to travel through. We talked about electromagnetic waves, which would be another form of light, and it doesn't need a medium. We know that waves are energy that's traveling in this form. And we also know that there are a few different types of waves, including the transverse, where the wave moves perpendicular to the direction it's moving, and then also longitudinal, where it moves parallel to the way it's moving. We also talked about the different parts of the wavelength, which is one point to the next point on the other wave, so it's one whole to and fro, or one whole cycle. We also talked about what the amplitude was and how that was related to energy. And we also mentioned about sound being a longitudinal wave. And we talked about surface waves. We started talking about frequency and wavelength, and that's where we're going to take off here today. So before we get into that, I'd like to throw in a little bit of trivia. So the trivia we're going to start with is about AM radio. So let me get this on screen. And this is just something that I find interesting, and I thought I would share it. If you're ever driving, and I don't know how many people listen to AM radio. You guys aren't old enough like me to listen to AM radio all the time. But when it's sunset, or just right after sunset, or just right before sunrise, weird things start to happen with your AM radio. You can get stations that you never knew you could get. So this is something you might want to try sometime. What happens is that the ionosphere reflects the radio waves back when it's dark. And so what happens is that the waves shoot up there and they bounce back and they travel a greater distance. And I know that when I wake up early in the morning, I get AM radio stations that I can never get later that day. And then also if I'm driving at sunset, I can get stations that I can't get. And what happens is they turn down the power of those because the AM radio stations start to intermix and it gets all weird. Okay. So AM stands for amplitude modulation. And let me get a little picture here. So we have waves, and what they're going to do is they're going to change. Modulate means to change. They're going to change the amplitude of the wave as it travels. FM is known as frequency modulation. So they're going to change the frequency of the waves, and that's the difference between the two. FM is much higher energy and delivers a better signal. And let's look at FM. So FM signals are called line of sight. And if you haven't heard that word before, it's just like it sounds. It has to be in straight line of the signals being shot. And so since the earth is round, you cannot get those signals for very long because we go off that curve of the earth. So one example, if you have a Columbus station, like say you're driving home from Marion and you're listening to one of the Columbus stations, it always ends up right about 294. I turn on 294, so that's why I know where this is, that the FM stations from Columbus go out. And what that is that curve of the earth makes it so the signal can no longer get to you. So that's FM signals. Now, a lot of you guys use probably satellite radio or XM radio, or you use, satellite dish for your TV. And it's also a line of sight, but they don't use FM signals for that. They use microwaves. And microwaves are just a little bit higher energy than the FM radio signals. So a little bit different signals. They all do the same thing. When they're starting now, they're changing into 5G. And 5G is they're using another range of radio waves where they haven't used much. And the lower range intertwines with the FM signals, I believe. All right, now we're not going to do a bunch of math in this chapter, and I said that already. So this was an older chapter that I had done, so I'm not going to really go over this, but we can calculate the speed of a wave with frequency and wavelength. All right, now to the new section. Wave interactions are the way that we tell how waves behave. There are a lot of these things that are real familiar, and you will have no problem with this stuff. So let's go on this. So we're going to talk about reflection, refraction, diffraction, and interference. And it's kind of interesting. I don't know. This is going to be a kind of chapter where I'm just going to talk about things that I find are interesting about waves, and hopefully you learn something about them, and that's what we'll do. That's just a cool picture, so that's why that's on there. Okay, reflection. Hey, I drew this picture. This was back before they had Google Images. I had to draw that. It was supposed to be a pool table, but when I transferred over to the different format, it messed up. So it looked really cool before. I know you don't believe that, but I'll say it. Okay, reflection. Reflection means that the waves can bounce off of a surface, and when they bounce off, the angle of incidence, and that angle of incidence is this angle that it's striking at. Incidence is when it hits, is equal to the angle of reflection. So if you look at the picture I have here on the side, it's a little bit clearer. This is the angle of incident, right? They always measure it from a line that goes perpendicular from the surface. Now, the reason they use a line like that instead of measuring this angle down here is because maybe the surface is warped. Maybe it's a curve. Maybe it's like a sphere or something like that that reflects. So if you measure perpendicular from the point that it strikes, that's always going to be the same, right? And so it just gives a better judgment, a better measurement. And so this is the angle of incidence, and it is equal to this angle of reflection. Now, a weird thing about reflection is the bigger this angle becomes, and that means the more angle that it strikes at, the greater the reflection is going to be. Good example, on a hot day when the sun's about ready to set, the heat waves coming off of the road, right, create a little bit different barrier, a different material. It's the air is a different density than the air above it because it's warm, so it's spread out, right? Hot air expands. And so when that light strikes that, it bounces off, and it gives you that illusion that it's bouncing off of something that's floating above the road, and it makes it look like it's called a mirage. It makes it look like it's water on the road. Oh, one of our common things that we know with reflection is the echo. And so you can use an echo to tell how far things are by counting how long the echo takes to get back. Here's our little guy yelling down, hello, hello, and it comes back up the well. And so you could measure distance with that. And what we'll talk about is how they use, some animals use echo, what we call echolocation, to find stuff. And also it's what we use when we talk about sonar and radar. Now, sonar's with sound, radar's with electromagnetic energy. So that's an echo. Now, something very closely related to the echo is called the reverberation. Now, the reverberation is the reason why you sound really good when you sing in the shower. Now, if you look at the bottom picture, the echo, the sound has a long time to get to that wall and back, right? And your brain has enough time to tell that it's a different sound, right? Or the waves are coming back. Now, say you're in the shower like this guy up here. I don't know if he's in the shower, but he's in a small room. The wave reflection is going to be so fast that his brain doesn't have a chance to tell the difference between the original wave and then the reflected wave. And so what happens is that it sounds fuller, like there's more sound there, because there is more sound because you're hearing both the reflection and the other wave. And reverberation may be a little button on your guitar amplifier that makes your guitar sound a little bit fuller. So anyway, that's why you sound better in the shower, because of that reverberation in there. Now, if you were going to be an engineer or a acoustic engineer, this would be a job. If you're trying to design buildings, say like the band room or a concert hall, you want to take into account the laws of physics, and one of these would be the reflection of those sound waves. So if you have very, very smooth walls, what happens is the waves bounce off exactly at those angles, right? And this angle right here doesn't quite look right, but yeah, maybe it is. All right, so they bounce exactly at those angles, and what happens is the sound doesn't get dispersed equally, and it sounds spotty and weird. So a lot of things happen. Say if you're going to become a professional musician, or you have to have someone who knows how to set up your sound system so it sounds good. It may sound good to you on stage, but you want it to sound good to the audience. And sometimes musicians, when they're on the stage, have trouble hearing what they're playing, or they have weird reflections that mess up the whole thing. Now, if you have rough walls, right, like the second picture, and if you've been in our band room, you know, it has like carpet up the walls, and it has those weird tiles on the ceiling. That's what they're doing. They're trying to disperse that sound. So there's all sorts of different reflections, and so it gives a better sound. All right? Does that make sense? If you've ever been to the movie theater, I know it's been a long time for most of us, but they have those weird curtains they always have weird curtains on the walls, right? And what those weird curtains do is they help diffuse that sound, and they give that sound something to bounce off that's not as solid as a cement block wall like most of those theaters are made out of. Here's another example. Like if you've ever been to a old auditorium, our auditorium, or a church, and the person up front doesn't even have a microphone, but you can still hear them. It's because the way the rooms were designed. They're designed to have that sound bounce off every surface and go out to the crowd. So it's kind of interesting if people are interested in that kind of thing, or you want to be a musician someday. It's something you might want to look into. Okay, this is echolocation. And echolocation is what bats and porpoises use to, and whales use this to find their food or find their way around. And so what's happening is the bat is releasing, that's that sound we just heard, high-pitched chirps. And those sounds will go off and bounce off the object, and it'll be able to tell how far it is, what distance it is from it, and which direction it's moving. And that's just from what we call the Doppler effect, which we'll talk about in a little bit. Now, dolphins also use that same thing. Let's see if I can get that sound to stop. Okay, and dolphins use that same idea to find fish in the ocean or find their way around. And actually, sound does travel better in thicker mediums like water, so the sound travels better in water. Side note, if you've ever been into the pool or in a pond and you took two rocks together and you clicked them underwater and it sounded super loud, that's because sound travels better. The particles of water are closer together than the air, and so the sound sounds better, or I shouldn't say sounds better, but it travels better in the water. Sound even travels even faster through solids. And that's why, I don't know if anybody told you this, but we used to put our ear on the railroad tracks. You shouldn't do this though. And then if you can hear the train through the metal of the railroad tracks, it travels much faster and better, and you can hear the train from a longer distance off. Okay, so that's echolocation. I would normally show a little video. Oops. That's not the one I thought it was. There we go. Okay, so I usually show a video that shows a man who was born blind, and he has kind of developed his own echolocation by clicking with his tongue, and it's usually a video we watch. We're not going to watch it this year because I'm not going to make you watch that over the thing. Okay, so echolocation. By the way, echolocation is sonar. So we've taken that technology, if we were watching the old movies and the bloop, 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 That's the beep of the sonar, and they use the same idea. They use computers to measure how long it takes to get back, and they can find things underwater. And it's the same exact thing they use for radar. And so radar is just radiation, or I should say it's microwaves, and they bounce off objects, and they can tell where planes are and things. What's that? You want to hear the exciting how they discovered microwaves and radar? Well, I'm glad you asked. When they were, I shouldn't say it that way, I said it the wrong way. When the U.S. government was developing radar, this is kind of a weird story. One of the scientists or engineers had a Snickers candy bar in his pocket. And while they were testing the microwaves in the room, his pocket got really hot and the candy bar melted. And he discovered that those microwaves were just at the right frequency. Remember what frequency means. The right frequency that they can make the water molecules or the sugar molecules vibrate. And what does that mean? When particles vibrate, that means they're hotter. They get higher temperature. And so what happened is this candy bar melted because of the radar. And he went on to make a famous invention. And they originally called it the radar range. And they now call it the microwave oven. Refraction. Okay. Refraction is when light bends as it passes from one medium into another. So as it changes from one medium into something denser, it causes those light waves to actually change speed. And so as they change now, light's the opposite of sound. When light goes into a denser medium, it slows down a little bit. And so it causes it to change these speeds. So let's first look at the first picture here. The old stick in the water. We would do a pencil in a beaker if we were in class. But what happens is that as it goes into the water, that part underwater, the light speed is changed a little bit. Now, your brain doesn't realize that the speed of light has changed underwater. And so what happens is your brain interprets that as the stick is not in a straight line, it's bent. This next picture, you might recognize this from the Pink Floyd album, Dark Side of the Moon, right? It's a prism, and it's making a rainbow. And so what's happening is the light strikes in this triangle shape. What happens is that each wavelength of light, those different colors, right, bend at a different amount. Now look at that picture. The blue is bending the most, the red is bending the least, and these other colors in between are bending in proportion to that same way. And so what happens is the wavelengths of the blue light, or the purple here, have the highest frequency. They're the shortest waves. They bend the most. And the waves on this side have the lower frequency, the longest wavelengths, the reds, and they bend the least. And so what happens as the light passes through there, those colors will separate up. All right. Now, an interesting fact here. This is the reason that the sky looks blue. Because as the light is passing from the sun through our atmosphere is acting like this prism. And it's causing this light to bend. And what happens? Well, we're down here, right? And so as the light passes through that atmosphere, it causes it to bend. The blues bend the most. And what do we see? We see blue light coming from the sky. Oh, sounds like somebody has COVID over there. All right. So then as the sun starts to set, what happens is we pass through this color range here. And you look at that green, look at that yellow, look at that red, right? That's like the sunset. And so as the sun passes to the edge of this, as we're just getting the very, very edge of the light that's getting bent, we see those colors of the sunset. So actually the sky is blue because of refraction. A lot of people think it's because of the ocean is blue. That is not the reason. It's because of the refraction of the sunlight going through the atmosphere. Now, I drew this little picture of the Jeep here. And the Jeep is driving, and it says the road, okay? And so think of this as a wave. So as we're traveling on a road, we can travel fast. But if you've ever driven off the edge of the road a little bit, and you go into the stones or in the mud beside there, it slows your car down on that slide and pulls you really hard off the edge of the road, right? So if you drive off the edge a little bit, your car jerks real fast towards the edge of the road like you're going to drive off into the ditch. Well, that's because the car can't drive as fast in mud. So think of this as refraction. So when it hits at an angle, the light strikes at an angle, the one side of the light strikes first, it causes it to slow down. Just like when the Jeep strikes the mud, the tires that are in the mud first slow down, and it causes the Jeep to turn a little bit. And then when the Jeep is completely in the mud, it'll straighten out because all the tires are in the mud again, right? If we were going out, the opposite would happen. When the tires hit the pavement, they would get traction and they would cause it to bend. Refraction works just like that. Oh, good, my animations are working. Now, your animations on your notes aren't going to work. I had to change the format to load it into Schoology. So I'm sorry about that, but you can see them here. Now, this is just another picture of this is the medium, this little line here. Think of this as a medium. It could be two ropes tied together. It could be two springs tied together. Anything like that. And so we have a denser one here and we have a lighter one. And so we're going to see what happens. When the light strikes and it hits the boundary in between there, what happens? Two things happen. The first thing that happens, well, I shouldn't say the first, they happen at the same time, is a small wave, a lesser wave, keeps traveling in that same direction. But it's lost some of its energy. It's lost its size, and it looks like it's slowing down because it's in a more dense medium. So it slows down, right? And then look also at the boundary here. There's a small inverted reflection that shoots backwards, right? A lot less energy than the original wave, but it comes backwards. So for you people who wear glasses, have you ever noticed that you're wearing your glasses, you see a little reflection every once in a while? You see your eyeball or you see your eyelash. It looks humongous and weird. This is because of the little reflection that occurs also when the light is striking the boundary. Here's another picture, and again, we have an incident angle, and that angle is always measured from, they're calling it the normal, but it's perpendicular from the surface. And so we measure from this side always. The light waves strike, and now normally you would show a picture where this would be also a light reflection coming off of there. Whoops, we passed it. And then this light right here is passing through the material. So say this is glass or this is water, and it's a denser material, so this is causing it to bend towards that material, right? And so look at the angle of refraction. So this is the refractive angle of refraction, and this is the angle of incidence, all right? So the light changes speeds and it causes it to bend. You can see this like if you look at glasses. Now, before you go, and this person down here has a lazy eye too, so we're not looking at that. We're going to look at the pictures behind the glasses. Okay? And so look here. This girl right here is farsighted. Or sorry, this girl is nearsighted. She can only see close up. This is like I am, and most of the people that have glasses are probably nearsighted, right? And so as she has her glasses down like this, you can see that it's causing her face to look smaller. That's because that light is bending in a little bit, right? And so that shows the bend of the light. Now this person here, and you'll know the people have glasses and their eyes look bigger when their glasses are on. Mr. Niederkorn is a good example of this, right? He has his glasses on and it makes his eyes look magnified. And the reason is because he's farsighted, and these lenses would cause the light to bend the opposite way. Nearsighted glasses make your eyes look smaller. Farsighted glasses make them look bigger. All right. Our next thing we'll talk about is called diffraction. And diffraction is the bending of waves as they pass through a hole. All right. And so think of this like the hallway. If somebody's out in the hallway out here and they yell, "Hey!" the sound still comes into the room and fills up the whole room. Right? It doesn't have to be line of sight. So waves will bend around little curves. Now there's a rule that tells how much they bend depending on how big the the hole is, but and how big the wave is. But for the most part, they'll bend through and they'll create a whole new wave. All right, interference. Let me see how much time I have. I'm trying to keep it pretty short. Ooh, we went too long. So I'm going to stop for today. It's been 25 minutes. So I'm going to stop, and we'll stop at interference. And I have more stuff with the interference coming up tomorrow.